Hello, welcome to this channel, Dr.arm'schemistry. Chemistry. Friends, we were discussing the synthetic methods of organometallic chemistry. Last time, we have seen the types of methods into two types. One was using elemental metals, and in second type, the reaction various compounds, chemical compounds of their types of desired nature. Now, these synthetic methods can be studied in different ways. One is by using the type of metal, such as main group metals, transition metals, alkali metals, alkaline earth metals, etc. And in the second way, the synthetic methods can be studied by considering the nature of nature of organic species. The organic species can be alkyl, alkene, or alkyne. Similarly, the aryl group is there, which is also giving us different types of synthetic methods. Similarly, carbenes, carbynes, etc. There are variety of sandwich type of compounds. So in this way, these are possible to be discussed, but we have to follow only one type of methods, so that it will be easy, or we can also discuss both types. So first of all, we will see the methods which are based on the type of alkyl groups as well as the use of alkali metals or alkaline earth metals or transition metals. So we will see some synthetic method or reactions which are carried out using metal in the elemental state. So these are discussed like this: using from elemental metal. So there are several methods, such as a reaction is carried out between a metal and alkyl halides or organic chlorides. Organic halides. So this can be generally represented as two metals react with NRX. So it gives the metal MRN plus MXN, MRN plus MXN, or we can also show the formation of twice R N M X N. Means this is addition product. So this provides an important and general method for the preparation of the organometallic compounds. Here we can use the metal or organic halide species. One of the interesting example of such preparation can be given here. For example, zinc is used in the elemental state, plus organic halide. We can take the example of CH3 CH2I. So this zinc can be taken in the form of a couple also, zinc, copper, couple. So in this way, the zinc can also be used here. So it gives CH3, CH2, Zn. Ethyl zinc halide. So here, if you see the thermochemistry of these reactions, it shows that the heat of reaction is positive, negative for all these reactions. Means the heat is evolved, or delta H is exothermic, that is heat of reaction, or the reactions are exothermic for the same group of metals or the metals of the same group. Then mechanism of these reactions and conditions at which these reactions are carried out are dependent upon the different elements. Means with the different element, the conditions of reactions and the mechanism of the reaction may vary. It cannot be the same. These reactions also took place or can take place using or on the basis of certain driving force. Is decreasing or increasing in the following order for the organic species, such as if we take NMe3 and N8, then PMe3. So here NMe3 has stronger driving force than PMe3. Here nitrogen and phosphorus, these are the species. Me is methyl group. So these N, P are of the same group. And next metal element is arsenic, AsMe3. Then next one is Sb, antimony, SbMe3. Then next one is bismuth, BiN8. So the driving force here is very high in case of DMI3, or in short we can see this driving force increases as a general trend as we move down in the same group. So if we take this group of nitrogen, phosphorus, arsenic, etc. So except that of these, the driving force is found to be increasing from arsenic or phosphorus to this bismuth. Similarly, if we take another group number 4. So there is silicon. So its driving force is minimum. Then CCH34. Then there is SN, CH34. Then there is PB, CH34. So the driving force is also here found to be increasing as we move down in the group of silicon. That is this group of carbon. Carbon, the next element is, as we move down, it is silicon. Then tin, but here there is some change in the order of this magnitude of driving force. This is the most common way of preparing the metal alkenes, that is organometallic compounds, by transmetallation reaction. So here the reaction is carried out between the transition metal halide. This using transition metal halide with alkyl or main group metal alkenes. Means the metal is taken in another form, not in the need not be taken in the metallic form, elemental state, but the metal for which the organometallic compound is to be prepared is taken in the form of its organic derivative. Means organic compound means already existing, is available metal organic species, that is organometallic compound. So this such type of organometallic compound is typically more ionic and reactive. That is why it is called a reactant. And these reactants are available commercially as per our requirement. So we will take the example of this CH3Br plus twice Li. So here we are using the metal directly as it is. So this gives the methyl lithium, that is CH3Li plus the LiBr. Then second example, here we are taking this reagent as lithium in the form of like this CH3Li. So the lithium reagent, this is the reagent, and we want to prepare here the organometallic compound of tungsten, WCl6. So as a result of this we get WNA6 plus LiCl. CH3 means Na. Another example is aluminium organometallic compounds. Here aluminium is taken in the elemental state. It is reacted with this NaCl, means CH3Cl. So after reaction it produces a mixture of the products like Al2, Cl2, Na4. So this is one part. Another is Al2, Cl4, Na2. Means these are reactions which are giving products like disproportionation reaction. Now out of this, if we take this, we get thrice Al2, Cl2, Na4. So when it is reacted with sodium metal, it gives twice Al2, Na6 plus twice Al plus 6 NaCl. So here we get this important product, that is aluminium complex Al2 Na6. Now we will see another examples. So if we want to prepare organometallic compounds, means alkyl gallium, then we have to use this gallium chloride GaCl3 plus the alkyl methyl thrice Na3Al. So it gives gallium, that is Na3Ga, Na3Ga plus thrice Me2 AlCl. Me2 AlCl. Then another example for the preparation of zircon organometallic compounds, we can use this zircon chloride ZrCl4. Means here we are mostly using the chlorides. Then if it is reacted with 4 PHCH2 MgCl, it gives the organometallic compounds zirconium CH2 PH4 plus 4 MgCl2. So this PHCH2, this carbon is attached to this zircon and we get this product. Then another reaction can be carried out in this way. Platinum compound PtCl2 PPH3 2 plus this so this Li is removed by these two Cl and we get this product. PPH3 plus twice LiCl. Similarly, the zinc alkyl products are obtained by zinc chloride plus twice Li. So this is the reagent. So it gives R2Zn as a product plus twice Li. Then if we take this, we have studied this reaction already, but we are taking it here and again C2H5I plus zinc copper couple. So it gives the product CH3CH2Zni. So after heating it, gives CH means ET, CH3CH2 means ET twice, Zn plus Zni2. Now we will see again some more reactions here. The next reaction is about the preparation of niobium organometallic compounds. So for this purpose we are using this chloride NbCl5, niobium pentachloride. Then when it reacts with Me2 Zn, it gives us the product Me2 NbCl3 plus ZnCl2. Then if we want to prepare magnesium alkyls, mercury alkyls, if we want to prepare mercury alkyls, then we can use this iodide, alkyl iodide plus Hg in presence of sunlight. it gives RHGI, RHGI. Then if we can also use here we have used mercury in the elemental state. We can also prepare this as Hg in the chloride form, HgCl2 plus RLi. So it gives RHgCl. So after again reaction with LiCl, it gives R2Hg. Now we will see the next point in this type of reaction, that is oxidative addition. In this oxidative addition reaction, our aim is to obtain the organometallic compounds. But when the oxidation reaction takes place in case of metal, the oxidation state of that metal is increased. For this purpose, the metal which required for this reaction should be in lower oxidation state, or the metal should be electron rich. The number of electrons present in the metal should be more. So after carrying out the reaction, some electrons are given out, that is the oxidation takes place. So for this purpose, we cannot choose the metal in which the electrons are 10, means higher oxidation state, means if the metal is present in very high oxidation state, then such reactions are not going on or taking place. So these reactions are useful for moderately electron rich metal sector, and it reacts with alkyl halides. For example, MLN plus R Br. So it gives R MLN Br. So these reactions centers are suitable only for electron rich metal and not suitable for these metals in already higher oxidation state. Next reaction we will discuss here, type of reaction is, that is second, is beta hydrogen elimination. So this is the most common side reaction of metal alkyls. These reactions are most common type reactions. This reaction is much more rapid if we consider the metals of transition group or block. But this is not so common for, means they are not so rapid for main group metals. So such reactions can occur. These reactions occur when there are some conditions. The beta carbon of alkyl group should have hydrogen atom. The beta carbon of alkyl group should have hydrogen atom. So this is first condition. Then second condition is that the metal alpha carbon, beta carbon and hydrogens, that is beta hydrogen. This is alpha carbon, then it is beta carbon and that hydrogen. So all these atoms, metal atom, carbon atoms and hydrogen should be present roughly in the coplanar conformation. Should have a roughly coplanar conformation. So because of this, the beta hydrogen is why it is required, because beta hydrogen is coming closer to metal. This beta hydrogen comes closer to the metal. Then third is condition. The vacant side of the metal should have the cis position to the alkyl group. The vacant site we will say, vacant site of metal should be cis to alkyl groups. Alkyl group. So if it is at transposition, then the beta hydrogen cannot come closer to the metal and there is no possibility of bonding between the metal and that beta hydrogen. So this is the main requirement. So we will see some examples. In addition to this here, one more thing is to be remembered here, that so this is to be noted that in these reactions are believed to be concerted. It means the breaking of carbon hydrogen bond, that is breaking of beta carbon hydrogen bond takes place simultaneously with the formation of metal carbon and metal hydrogen bonds. Means when the beta hydrogen, the carbon atom attached to this beta is called beta carbon. So that beta carbon bond is that beta hydrogen and this beta carbon hydrogen bond breaking takes place simultaneously with the bond formation of metal carbon and metal hydrogen. So that is why it is called, this is called concerted reaction. Now we will see the example. So if this is beta carbon, it is attached to this one hydrogen. This is second hydrogen. There is third hydrogen and another carbon is there, that is alpha hydrogen. So it is attached to the metal, then to the another hydrogens. Like this. So if we see, so this is the alkyl organometallic compound, but we are showing that this is alpha carbon and this is beta carbon. So the hydrogens attached to this alpha carbon are called alpha hydrogens and these are the beta hydrogens. So all these this hydrogen, this is the hydrogen which is required in this reaction. So this hydrogen, this carbon and this metal should lie in one plane, that is syncoplanar. So this is reversible reaction we can show. So these are the hydrogens. So this metal carbon bond is slightly weakened and this hydrogen is coming closer to this metal. So this bond is, carbon hydrogen bond is also undergoing breaking and this metal hydrogen bond is undergoing formation stage. So this carbon hydrogen bond is breaking and this bond, metal carbon bond is under the process of formation. So after this we get this carbon hydrogen bond is completely broken. As a result of this, hydrogen is attached to the metal and this metal is further attached to this double bond. This bond and this bond are coming closer. Here means the electrons of these bonds are concentrated on this, means sigma and pi electrons are coming here and so after the complete transfer, so this beta hydrogen is completely transferred to this metal. So this bond is, this hydrogen is moving away in this direction and this is coming closer to this metal. So as a result of this, the beta hydrogen is completely attached, means this metal hydrogen bond is completely formed. So this is also a reversible process. Now if we see the stability of this beta hydrogen, means under which conditions the beta hydrogens are stable, means they are not capable to undergo the beta hydrogen elimination reaction. So these beta hydrogen reactions are not possible when the alkyl groups do not have beta hydrogen. If the alkyl groups, say if there is the carbon and there is no beta hydrogen available, then this reaction will not take place. For example, if we take the pH CH2 group, then here there is no beta hydrogen. Again, if we see another example, that is Me3CH2. So this is alpha. This carbon is alpha and this is beta, but the beta carbon is attached to the 3 methyl groups, so there is no hydrogen. And another example is Me3SiCH2. So this is also not having the beta hydrogens. These reactions are not possible when the beta hydrogen is not capable to reach the metal. This is this hydrogen and it is not possible to reach to the metal, or the elimination results in an unstable alkene. So there is formation of this alkene product. This is alkene. When this alkene product is not possible to be formed, then beta hydrogen will not, elimination will not take place. For example, in case of chromium Cr alpha, here L is equal to tertiary butyl or 1 norboronyl. 1 norboronyl. So in such case, there is no formation of this product with beta hydrogen elimination. Similarly, when this plane carbon, metal, hydrogen and this is not coplanar, syn coplanar, then there is no possibility of formation of such reaction, that is beta hydrogen elimination, and which gives alkene, metal alkene products. Similarly, there are also some examples in which the metal has shown that metal has firmly bound to the ligands. In some cases, metal is bound to some firm ligands or firmly with ligands, where the beta hydrogen is not available very close, means the metal exists in higher oxidation, higher coordination number. Metal exists in higher coordination number. For example, if we see this is the ligand, and for example it is the complex of beta, platinum, and here so with respect to this is alpha and beta. This is alpha and beta. So this carbon, beta carbon has hydrogens much away, far away from this platinum, so it cannot form beta elimination product. So if we take the norbornene example, titanium, this is one titanium, one norbornene. So in such case, the formation of reactions of this beta hydrogen elimination is not possible. So we will stop our discussion here, and next time we will see the synthesis of CP based sandwich compounds. So if not subscribed, please do subscribe and also press the like button and keep watching. So thank you very much.